now? Yes. Okay. Great. So I decided even in a session nominally on quantum simulation, a useful starting point actually is to think about quantum metrology, which is a field that actually shares the challenge of controlling and characterizing many particle entangled states. So the starting point for my talk is actually the realization that with our improving control over quantum systems, we have the exciting possibility to begin to think about going back in time. So what do I mean by that? I don't mean waking up earlier and beating the traffic from Stanford to Berkeley so that I could have made it to the first talk this morning. But what I mean is that in the well-controlled quantum systems that we're beginning to assemble in the laboratory, we potentially can think about, in some small controlled system, actually switching the sign of our Hamiltonian, and which really allows me to effectively evolve in time forward and evolve in time backwards. What could you do if you could do that? Well, there are a couple of reasons why this might be interesting. One is it may tell you something about the system that you've built. So in particular, if I don't quite perfectly go forward and backward in time, but have some small perturbation in between, this might tell me something, how close I come to returning to my original state might tell me something actually about whether the system is, for example, chaotic, right? And this is this classic idea of a Low-Schmidt echo as a probe of sensitivity to perturbations, a diagnostic of chaos. On the flip side of that, if I understand my system already very well, then this type of a sequence of evolving forward and backward in time might actually give me a way of sensing a small perturbation if I don't return precisely to my initial state. And so these are actually two things I'm going to talk about today. And particularly, I want to talk about what role many-body entanglement plays in this type of a scenario. And the reality that while we never actually will perfectly go back in time, there's always dissipation in real quantum systems, is approximate time reversal still a useful concept for these types of applications. And my model system for thinking about this is going to be a system of cold atoms in an optical cavity. Okay, so why do I like this model system? We're going to have a system of cold atoms that can interact essentially by exchanging photons, talking to each other via a light field in an optical cavity. And this gives us a type of interaction that is easy to switch on and off and control the sign of. And it gives us a system where we actually have a very quantitative understanding also of the interaction to dissipation ratio. And because we can have an interaction mediated by light, photons can convey information over distances. This is something where we can have a non-local interaction, which is convenient actually for generating entanglement on mass. And also, because of its non-local character, can potentially enable new types of quantum simulations. And so in the course of my talk, I'll first give a little bit more background on this type of interaction. And then I'll give two examples of how an echo type of measurement involving going forward and back in time can be useful in the context of one, quantum metrology, and two, quantum simulation. In the quantum metrology context, we'll be particularly interested in engineering quantum-enhanced sensors that are robust to noise. And in quantum simulation, I will go out on a limb and speculate about the possibility of studying in the laboratory quantum chaotic systems that might actually tell us something about black holes. Okay, so let's start, though, with the physical system that I'll be focusing on for my talk. I told you that we'll be thinking about atoms that can somehow interact by their coupling to light. And so the physical system I'll have in mind is one where I have some atoms in this cavity. I can shine in light, and any particular atom, these are some two-level atoms, I'll represent them as spins. Any particular atom could absorb a photon, emit it into this resonator, and another of these atoms could rescatter that photon. And if I have a process where when in that scattering the atom flips its spin, right, then I can get some pairwise correlated spin flips that will generate interactions among, in principle, arbitrary pairs of atoms. So this is a really unique type of interaction that's different from the local interactions one normally has in nature. In principle, with spatial addressing, one could imagine letting arbitrary pairs of atoms interact. Importantly, in this type of a process, there's a laser frequency. Simply by the frequencies of these control fields, I can actually tune the sign of the interaction. So in particular, there's some four-photon process, and there's a detuning that I can use the sign of to control whether these spin-spin interactions are ferromagnetic or anti-ferromagnetic. And the last thing that will be important is that if I can make my cavity good enough, then it should be possible for these interactions to be very coherent. Okay, so that is kind of the dream, is having this new type of interaction. And what do I mean about making my cavity good enough? Well, the key requirement for being able to explore this type of physics is that we are going to need to have a situation where an individual atom in the cavity is strongly coupled to an individual photon, and that means that the cross-section of this mode should be very small, the mode should be tightly focused, and the mirrors should be very reflective. Okay. At the same time, we want something where we can control these interactions and send light in from the side. And it turns out, actually, that combination of features is not so easy to achieve, but it's something that we've been doing in the laboratory, and so something that we've recently set up is a resonator where we have two mirrors that are separated by almost twice their radius of curvature, and the mode in the middle comes almost to a point. Okay, it's not exactly a point, it's about 10 microns, but this is small enough that we can have a combination of a very strong coupling to the light in this region, and at the same time, the optical access we need to have very versatile control of these interactions. Okay, so this is kind of the experimental setup that we have recently built in our laboratory, and this is what you see are two mirrors mounted on some piezoelectric stages that give very fine control of the tip and tilt, and allow us to achieve the very sensitive alignment needed to have very strong coupling and a nice big window to control the interactions. And at the end of the day, what this gives us is something where when an atom scatters a photon into this mode, the probability that it will interact with another atom is about 50 times higher than the probability that will be lost. And so this is an exciting regime of strong coupling cavity QED that will allow us to explore these types of photon-mediated interactions. So just to kind of, illustrate one more time, we have atoms in this resonator. We can see them scattering light into the mode, and the next stage is to actually control this scattering well enough to get those spin-spin interactions. I won't show you data from this setup yet, but we already know something about what we expect to happen. In a simple limit, which I'll explain to give you sort of a physical picture of some of the physics that can go on. So this, again, the one simple thing you can imagine doing is generating these kinds of correlated spin flips. And the Hamiltonian that gives rise to from possible processes of flipping one spin up and the other spin down in correlation, or flipping two spins up together, the net effect is some Hamiltonian that basically is an Ising-type interaction where the x component of one spin wants to align or anti-align design with the x component of another. So that looks something like this. And in the simple case where all atoms are equally coupled to the mode, that turns out to be something that I can represent simply actually as a nonlinear Hamiltonian as a function of the collective spin of the ensemble. So in this simple limit, I can actually then have a nice way of visualizing quantum states in the system as some spin with some uncertainty in where it's pointing. There's a quantum uncertainty because it's a finite quantized spin. I'll represent that by this sort of fuzzy blob. And the simplest thing that can happen here is that due to this nonlinearity, instead of this blob simply precessing about the x-axis, it can precess at a rate proportional to Sx, and this uncertainty can become squeezed. Okay, And so this is actually something that has been demonstrated, this type of dynamics, this nonlinear spin Hamiltonian, in a variety of different physical systems, Bose-Einstein condensates, where the interactions are true collisional interactions, ion traps with phonon-mediated interactions, and also in the cavity QED setting, where the interactions are mediated by photons. Okay, and in particular, so these are data from a number of years ago from actually a cavity, even in the weak coupling regime, where one can see that as one applies more and more light to the system, one starts with, this is kind of a tomographic reconstruction of the shape of the state one has. One starts with something that's circular, and this quantum uncertainty gets redistributed into something that is squeezed. And even so these experiments were actually done in a regime of much, much less coherent interactions than the setup I just showed you. But even in this regime of dissipative dynamics, this is something that gives useful entanglement and has actually been used to enhance the precision of atomic clocks. So this is just an illustration of Ramsey spectroscopy, where the uncertainty in the measurement, in the phase measurement, is enhanced by the fact that the quantum uncertainty has been reduced by this nonlinear interaction. Okay, so this is something that we demonstrated a number of years ago at MIT, and that has been really pushed now by orders of magnitude to have really, to be able to improve atomic clocks by an order of magnitude or more in recent experiments in the Kasevich group at Stanford. Okay, so quantum metrology is something that works. We've been able, in a number of experiments in various physical platforms, to perform measurements that are enhanced by entanglement. And this is kind of just to give an idea of the state of the art, just a smattering of different experiments that have been done. This black line here is the best measurement that could be done without entanglement. This red line here is the fundamental limit. And one thing that we'll notice is that we have, on the one hand, seen dramatic enhancements, but there's very, very much room to improve. And so one of the questions we're very interested in my group is actually, what would it take to push these things to that fundamental Heisenberg limit? Okay, well, it's not easy. And the reason is that that fundamental limit really is set, if I'm thinking about the example of measuring a phase, measuring time, it's set by the energy-time uncertainty principle. And reaching it requires, to have a very small uncertainty of time. In time, we need a very large uncertainty in energy. Okay, so what's a state with a large uncertainty in energy? If I'm thinking about spins, it's some kind of a macroscopic superposition of all spins in the high energy state or all spins in the low energy state. Okay, so this would be called a GHZ or a Schrodinger cat state. And it should be sort of intuitive that this type of macroscopic superposition state is something that is hard to prepare, particularly at large atom number. And I'll also raise the point that this type of state is hard to detect. And so something we thought about is, are there actually easier alternatives to approaching that fundamental limit? But first, let me just say, so what's kind of the state of the art in preparing this type of state? Well, it turns out actually that type of a nonlinear Hamiltonian that I showed before has actually been used to prepare these maximally entangled cat-type states of up to 14 ions using phonon-mediated interactions. And just to illustrate that one more time, what's required is a very, very, very coherent version of this type of twisting evolution that gives rise to some sort of interferences that eventually make us start from this spin pointing along towards us and end up with a superposition of the spin pointing in two opposite directions with some interference fringe that gives rise to enhanced interferometric sensitivity. Okay, so challenges with scaling this are that it requires this very long coherent evolution time. This type of state is useless as soon as we lose a single atom. It completely decoheres. And related to that, actually detecting it requires the ability to detect individual atoms, and in fact to detect the parity of this collective spin. Okay, so all of these are challenges, and I want to particularly say a little bit more about this challenge of detection. Quite generically, there's a sort of standard procedure for classical spectroscopy, which has been extended to quantum-enhanced spectroscopy, which involves preparing some kind of entangled state, letting it, so in this simple case of classical Ramsey spectroscopy, this is some state that's in the equator of the sphere, letting it precess, and then after some time, performing one more rotation and reading out the distribution of spin projections along some axis. Okay, and that same type of procedure has been applied with states with squeezed quantum noise, with other types of non-classical states illustrated here, including these small maximally entangled cat states. And whenever you do this sort of prepare a state, let it evolve, and then detect, in this case, an entangled state, the best precision you can get in this type of measurement is going to be limited by your detection in a way that actually gets, in some sense, this not only does it become harder to detect the state, the more sensitive it is, but this is actually a plot here of the quantum enhancement as a function of the uncertainty in detecting a state. And one thing you'll see is that, okay, the blue is the classical unentangled state, reaches just the standard quantum limit. But as we make these states that are more and more entangled, like this maximally entangled state, not only do we need a very, very low detection noise to obtain the full benefit, but at some point it actually does worse than something like the unentangled state or the squeezed state. So there's really, it would appear from this plot that maybe there's some fundamental trade-off between on the one hand, if we can make this highly entangled state, only if we can detect it perfectly can we benefit from it, and at some point, if our detection is imperfect, it might do worse than the unentangled one. So the question you can ask is this really fundamental, or can one actually make a highly entangled state that is also easy to detect? So this brings us to asking, do we really have to directly detect the entangled state, or is there another way? And I suggested at the beginning of my talk that another way might be to make some entangled state, so have a system evolve into an entangled state, perturb the system a little bit, and then see whether after that perturbation we come back to the initial state. So what happens if we try this actually with precisely that type of twisting interaction I showed before? Prepare an entangled state, perturb it a little bit, and then try to untwist the state by flipping the sign of our Hamiltonian. We can do this with these light-mediated interactions. Well, what we see is that initially we'll get something that's squeezed, or maybe even something that's non-Gaussian and wrapping around this sphere. If, in this case, I'm imagining perturbing it by a small rotation about the y-axis. So it's a little hard to see, but the whole state is shifted up a little bit. When I try to untwist this, something quite remarkable happens. If the state was perturbed, was shifted up a little bit in this step, then actually that perturbation will be amplified into a very, very large spin precession in the untwisting process. And so this small perturbation actually becomes very easy to detect. So I'll just illustrate that even a little bit more schematically, right? If I have this quantum noise gets sheared out, if I shift this state a little bit and try to unshear the state, there's kind of a long lever arm that moves this small rotation into a large displacement. And the final state is something very similar to the initial state with a large quantum noise that's easy to detect. Okay. And so the upshot of this is that if we imagine performing this sequence, we can look at a few different things. One is, as a function of how strongly I do this twisting, what is the intrinsic potential of the state, given by the sort of amount of entanglement in the state? That's this blue curve here. And it tells us that actually, if we wanted to make that maximally entangled cat state that involved twisting and twisting and twisting around, we would have to take a time that is very long. So in some units, this strength of the twisting scales actually with the number of atoms. And okay, so that's here. That's how long it would take me to make this maximally entangled cat state that reaches the Heisenberg limit. On the other hand, I can evolve for a root n shorter time and be almost as good in terms of the intrinsic potential of the state. It's a numerical factor, square root of E works. Aside from that, what I've done is, if I do this now in this type of an echo sequence, so this is the intrinsic potential of the state, but now I can ask, what is the actual sensitivity of this particular measurement procedure? And I'll find that in this echo, because I amplify the small perturbation, I will actually be able to benefit very easily from this large metrological gain. And so the red curve is actually the performance of this echo procedure. And so it comes very close to the Heisenberg limit. It doesn't require this very, very long coherent evolution time, and the state should be easier to detect. Okay, and the optimal state, it turns out, is not a squeezed state, but it's actually something that started to wrap around the sphere and is non-Gaussian, and that I wouldn't be able to simply detect in standard Ramsey spectroscopy. Okay, so there are a couple of really cool features of this scheme. It reaches a Heisenberg scaling after a very short coherent evolution time, but importantly also to detect that state and to benefit from that near Heisenberg limited resolution, I don't need to resolve single atoms. I only need a measurement that has a resolution on the order of the quantum noise of the initial unentangled state. And so looking at this type of plot again of the metrological sensitivity as a function of my atom number resolution, what I find is that whereas that Schrodinger cat state would become useless as soon as I have a detection noise on the order of one atom, this oversqueeze state that is easier to prepare is also something that can be detected even if my measurement can only resolve root n atoms. So I have a benefit in terms of being more robust to dissipation in the preparation procedure and more robust to any kind of detection noise. So this type of concept actually, we convinced our colleagues in the group of Mark Kasevich to try something very similar. It's not precisely this echo scheme, but a similar approach of using interactions to enhance the readout in a cavity-based entanglement experiment. And at the level of working with spin squeeze states, they were in fact able to detect something that was 8 dB squeezed, 8 dB beyond the standard quantum limit, even with low resolution fluorescence imaging that could not have otherwise detected the quantum noise. And so this is a really exciting application of this general approach of interaction-based readout. There's still some room to push this towards the vision of getting close to that Heisenberg limit and really making those optimal non-Gaussian states. And so we're excited about the possibilities of strong coupling cavity QED. But again, this type of interaction is quite common in a variety of physical systems. And these oversqueeze states have recently been compared in ion penning traps. And another really exciting possibility that we're thinking about is engineering interactions by coupling to Rydberg states for atoms in an optical lattice. This is something that's been proposed as a way of enhancing optical clocks. So these are places where this concept of having interactions of switchable sign gives really a new way of detecting highly entangled states and harnessing them in quantum measurements. So, you know, this twisting and these oversqueeze states are actually just one application of this echo concept, right? So, and there are other physical schemes that could also be used that exploit this general idea. It could be mapping a superposition of a single qubit to a macroscopic superposition of an ensemble, letting that sense something and mapping the information back onto the qubit. That's another example of an echo-type scheme that's been proposed and is naturally suited to exploring in cavities with non-local interactions. And beyond applications to quantum measurement, we've been thinking about whether this ability to switch the sign of the interaction is something that will be useful for studying quantum chaotic systems. So these are all ideas that had been kind of floating around in our minds when I received an email from my now collaborator, Brian Swingle. And Brian asked me the question about whether I knew of a physical system where I could evolve backward and forward in time, where I could have some kind of a control qubit that influences an ensemble, and he said he was thinking about diagnosing chaos. And I thought, that's interesting. We've been thinking about these same things. So why did he want to do these things? Well, Brian was actually thinking about a problem that I knew nothing about at the time. And that is the problem of information scrambling in black holes. So the question is the following. Let's say I have some many-particle system, and I want to ask the question, if I perturb a single qubit, how long does it take for that perturbation to propagate over all degrees of freedom? And there's a conjecture that there's a fundamental bound to how fast this can happen, which is saturated in black holes. So why can you even think about quantum information in black holes at all? This comes from a deep connection called gauge gravity duality between quantum many-body systems in some number d spatial dimensions and classical field theories in one additional spatial dimension, which comes about, roughly speaking, from the structure of entanglement in the quantum system. So the question that Brian was asking is, can we realize quantum many-body systems in tabletop experiments that are dual to black holes? And that's a hard question, so we asked actually the simpler question, if we could, how would we know? So this is where we come to this conjecture. The conjecture is that there's a particular time scale that's the fastest that information can possibly scramble in any system. And that time scale is essentially set by the log of the entropy of the system. Okay, and the intuition why it should be set by the log of the entropy you can think of by thinking about a system of n qubits and saying how fast could I make information spread from one to all? Well, the fastest I could do it would be by kind of a stepwise connecting random pairs of these qubits. And if I do that, then the log of the number of qubits, log 2 of the number of qubits, will tell me how long it takes the information to spread. So this kind of a notion suggests that a natural candidate for seeing this type of fast scrambling would be some kind of a chaotic model, right? Somehow I want information to spread quickly. And the way of characterizing chaos in a many-body system, in a sort of intrinsically quantum mechanical way, is to ask how fast commutators grow. So I have some like simple operation, like a spin rotation, the rotation of another spin, and the question I want to ask is how fast, ordinarily these should commute. These are separate spins. But if I have interactions in the system, then maybe they'll make these operators fail to commute if I consider flipping this spin at some time and rotating this other spin at some later time. Okay, so the type of experiment you'd like to be able to do is to compare the possibility of two possible sequences. One, I perturb some spin, and I allow my system to interact, and then at a later time I perturb another spin. Or I allow my system to interact, at some late time I perturb that second spin, this is W, and then I go back in time and perturb the first one. So just another way to think about this is the top branch is me giving this talk with all the slides in the right order. The bottom branch is me skipping an important slide at the beginning and then coming back to it at the end. And because they were out of order, you'll be sort of confused. In the first case, you're happy. In the second case, you're confused. And we want to basically measure the overlap between these two situations. So this is basically the overlap between two different many-body quantum states. And being able to compare these requires the ability to perform some kind of many-body interferometry. It also requires us to evolve our system forward and then backwards in time. I should say there's at least one alternative that's compelling that's been proposed by Norm Yao and Dan Stanford and others here at Berkeley. But this is the scheme that Brian was thinking about when he asked me whether I had a way of engineering a control qubit and reversible time interactions. And so I think I'm running out of time, so I'll just jump ahead quickly and say that that the cavity QED setting is a natural implementation. And it's particularly intriguing for two reasons. One, that we have these non-local interactions, which are kind of what featured when I showed you this diagram of how we would expect scrambling to happen quickly. Right? I was connecting these random qubits. And while in principle we can have some complex graph of non-local interactions, we can also start with something that's simple to understand, which is always good for benchmarking one's quantum simulator. And that's something where the interactions are global, and we can actually do some calculations on a system of hundreds of spins. And so we just did a few calculations thinking about a chaotic model that can be realized with these global interactions. And the key point one can take away is that the time scale for the growth of this commutator is indicated actually by the decay of the correlation function that I've called f, which is shown in blue here. And it's a time scale that intriguingly actually grows with the number of degrees of freedom in the system, right? I said there should be some growth with the entropy of the system. And this is very different. I was comforted to see this because this is very different from what you'd expect if I just have some other decoherence mechanism, right? And so there's really kind of a signature of this scrambling that one could hope to see in an experiment. That's this growth of the time scale, and one can quantify this time scale and ask the question, is this a fast scrambler? Can we make a system that reaches that fundamental bound? Somehow I keep pressing the wrong button here. Second thing we asked, because we were able to solve the system exactly, is can I really still see this if I have some dissipation? Right? I'll never perfectly go back in time. Nevertheless, one can actually see, even in a realistic dissipative system, a distinction in timescales between this growth of the commutator and the decay of more normal time-ordered correlation functions that have nothing to do with this scrambling of information. Okay, and so this is exciting. There's in the sense that there's really a fundamental timescale for quantum many-body dynamics that people have been thinking about in the context of black holes that just now is becoming experimentally accessible in tabletop quantum systems. There have been actually a few related experiments recently in ion traps and in NMR systems, and there's really kind of a smoking gun signature that this scrambling is what one is detecting if one sees this kind of timescale that's growing with the number of degrees of freedom. I talked about non-local interactions that one could realize in a cavity, but this concept is very broad and could also be applied to study a number of interesting questions about the propagation of information in systems with local Hamiltonians and distinguishing different types of many-body phases. So just to summarize, I've shown you two applications of the new possibility of engineering quantum systems where one can go back and forth in time. On the one hand, to novel quantum simulations that might enable us to probe the physics of black holes in tabletop experiments, and on a sort of more applied, in a more applied direction for precision measurements, accessing entanglement, fully benefiting from entanglement that would otherwise be difficult to see, to make quantum sensors or quantum clocks robust to detection limits. So with that, I'll thank my students, Emily and Greg, on the cavity experiment, who are involved also in the quantum metrology theory, and Brian Swingle, in particular, my collaborator, on the information scrambling.
Monika, we have time for one quick question while Peter Mounts is setting up.
So just to be clear, this is that's theory. The approaching the Heisenberg limit was theory. So, okay, so there's theory on what should be possible. And this is this scheme for approaching the Heisenberg limit, even in the presence of large detection noise and at a significantly shorter coherent evolution time than for making these cat states. Yeah. Yeah. Mm-hmm. So I think the important thing is that it depends actually what state you're using, and this is really the neat thing, is that if I'm trying to get to the Heisenberg limit, I need this Schrodinger cat state, but I can get close with other states. And so one of the key points here is that to make this oversqueeze state, the time to prepare the state. So I think it's an important point to make that so there are sort of two different phases of this type of an experiment. One is preparing the entangled state, and then there's the sensing phase. With cold atoms, actually sort of holding onto the atoms and not losing one in the time that you're making the measurement is not necessarily the biggest challenge. The biggest challenge is actually preparing the state where you need some interactions that are accompanied by some decoherence. And so if I don't need to apply my interaction for as long a time to make this entangled state, then I'm actually more robust also to decoherence that accompanies the state preparation process. So one of the neat things about this is I don't need as long a coherent evolution time to make this oversqueeze state. as to make a cat state. And so with realistic interaction to decay ratios, that oversqueeze state is more accessible, and the numbers, the calculations we've done for systems of order 100 atoms by a couple of different methods, the strong coupling cavities or Rydberg dressing, that state can be prepared without loss. Yeah. So during the evolution, and okay, so the one, sorry, I think you want to get to the next speaker, but I think I want to add one more point, which is that during the evolution, you're very sensitive to phase noise, let's say. That's precisely because this is a good sensor. So what you need to be careful about, right, is, of course, if I'm trying to sense to make a clock, then I shouldn't be sensitive to magnetic fields, let's say. But that. So. Yeah, maybe, okay, we can talk about this more later, but I think the key point is that that sensitivity to phase noise is sensitivity to the thing you're trying to measure. But there are sensitivity to loss, for instance, is a separate problem. Okay, yeah.
Okay, our next speaker is Peter Mounts from Sandia National Labs in Albuquerque, and I guess he's going to talk about their trapped ion efforts, and in particular quantum information processing in scalable microfabricated ion traps. Please, Peter.